Hey guys, today we'll talk about acceleration in rotating reference frames. And of course in the language of engineers. Basically there are three kinds of acceleration. Acceleration could either be radial or tangential or Coriolis. Coriolis acceleration is a weird one based on disagreement between reference frames. Whereas the radial and tangential components are responsible for the conic path followed by the object. Now let's see what these components represent. Say you are spinning a stone with the help of a string in the clockwise direction with an angular velocity omega. In such a case, the radial acceleration is pointing inwards towards the driver, which is your hand, because you are pulling an object that's trying to go straight, by which it traces a circular path. As you speed up your spinning, tangential acceleration comes into play, which is nothing but the tangent to the circle at the stone's position, at that instant, directed to the right, as our motion is clockwise here. The radial acceleration is nothing but the fancy name for the centripetal acceleration v squared by r. It's responsible for keeping the stone in the circular path. But this tangential acceleration r alpha comes only when there's a change in how fast you spin. Because this alpha is the angular acceleration, which is nothing but the time derivative of the angular velocity. Now this could be 0 when you are either at rest or spinning at some constant omega. This directly influences the tangential component. It becomes 0. But mind you, the radial component is still there. Again, that keeps the stone in its circle. Now to the weird Coriolis Force. Question: what happens when you throw a ball while you are spinning around? This happens. Okay, let's say we are riding a merry-go-round and I am shooting the balls from one end, while you are at the other end trying to catch them. Will you ever catch them? Nope. The path of the ball curves. You'll definitely miss the ball unless I throw it very fast, because you would have moved sideways between the small interval of time. As a matter of fact, the turbulence in our Earth's atmosphere is caused by the very same effect, due to the rotation of the Earth, of course. This is the Coriolis Effect. You can Google for more. Okay, that's enough physics. Let's take a driving crank OA with a clockwise angular velocity. It has a slider B attached to it. This slider is constrained only to move along the crank, up and down. Assume that the slider has a velocity in the upward direction. This looks very analogous to our ball throwing experiment. Slider is the ball and crank is the merry-go-round. The direction of this force is important because it resembles the tangential acceleration of the crank, by the direction at least. We'll talk about that in acceleration diagrams. Anyways, there are 4 cases to the direction of Coriolis force, but one case is enough to analyze the others. If the velocity of B is upward and OA rotates clockwise, then the Coriolis acceleration acts to the right. It's a cross product. Coriolis component acts normal to the plane containing omega and v, and so we follow the right hand rule. If the index finger gives the direction of velocity and the thumb represents the direction of angular velocity, then the middle finger is the direction of Coriolis force. This means that the direction of Coriolis component changes whenever omega or v changes, but not both. If both change, we get the same direction again. You might be wondering how the angular velocity vector actually points in a direction. It's rotational, right? It's either clockwise or anti-clockwise. How shall we represent that with our thumb? Well, we have a convention for that, given by the right palm rule. If the fingers point in the direction of the curl of omega, then the thumb indicates our convention. Yeah, it's up when omega is anti-clockwise and down when it's clockwise. Don't know who chose that way. Thank you.